Hi everyone, my name is Brian Yu, and we're about to start production here on an introduction to artificial intelligence. We're going to be filming all week, so if you'd like to tune in live today or later this week on YouTube, you're certainly welcome. This course will soon be available as an introduction to artificial intelligence. So we'll be started in just a moment. Hello world, welcome to an introduction to artificial intelligence. My name is Brian Yu, and in this class we're going to be exploring the ideas and the strategies and the algorithms that computer scientists have developed in order to build computers that can behave intelligently. Ultimately, the goal is to give you a sense for what artificial intelligence, or AI, really is, how it is that these technologies work, what they're good at, and what their limitations are. So we can start by trying to ask, what even is artificial intelligence really? And as we're thinking about artificial intelligence, it's helpful to start by thinking about our own human intelligence. What is it that makes you or me intelligent? Well, we have the ability to acquire and use knowledge and skills. We can solve complicated problems. We can experience the world and learn from that experience. And so artificial intelligence, or AI, is really about taking those same capabilities and putting them inside of a computer. So a computer can do all of those same types of things, solve all of those same kinds of problems too. And this little robotic duck here will be our representation of AI that we'll use throughout the class. And we'll be exploring a wide variety of problems that AI might try to solve. So what kinds of problems are we going to try to solve? Well, we'll start by taking a look at AI playing games. This was one of the earliest areas of research into AI, where we were thinking about questions like, could we take a game like chess, a complex game that requires a lot of human thinking and strategy, give it to an AI, and have AI figure out a strategy of its own, figure out what good moves to play would be in any given position. And then we'll take a look at how we can use AI to make predictions. Modern AI makes all sorts of different kinds of predictions in our lives every day. For example, when you get a phone call, sometimes your phone might automatically flag that call as spam. It doesn't know for sure whether it's spam or not, but it could say that spam might be likely. It's making a guess. It's making a prediction. And we'll talk about strategies that AI can use to be able to make good predictions. We'll then look at how AI can try to analyze data. For example, you might have experienced AI on a movie streaming or TV streaming website where it sees the movies or television shows that you've watched, and then by analyzing that data, it's able to come up with some recommendations for you, things that you might like to watch in the future. And we'll talk about some of the techniques that AI can use to be able to solve problems like that too. And then we'll take a look at how AI can sense the world. That when we think about our own intelligence, we have the ability to sense the world, whether by our eyes or our ears. We experience the world and we draw judgments and get information from that experience. And we might think about how could we build those same capabilities inside of a computer too, so that a computer could look at a photograph or maybe images of hand-drawn letters and numbers and be able to make sense of the things that it sees or the things that it hears. And we'll talk about how AI can sense the world as well. And that then will lead us into the problem of communication. This is an incredibly complex problem. Sorry, said that wrong. Let me back up a moment. I'll go back here. So you and I use our eyes and our ears. We experience, we sense the world. So we'll take a look at how AI can solve similar kinds of problems, where AI might be able to look at an image or look at a hand-drawn digit of a number or a letter, for example, and figure out what's in that image, use that information that it's sensing to draw some conclusions. That then will lead us to the problem of communication, an incredibly complex problem, where we think about how it is that you and I communicate with each other. We use language, we use words, we construct sentences and paragraphs, and a question will be, how could we build those same communication abilities into a computer too, so that AI can communicate with us, so that it can answer our questions and solve other kinds of communication-related problems. Then we'll take a look at generative AI, where we can think about how AI can generate new data of its own, whether it's generating text or audio or images or videos. We can talk about the strategies that AI uses to do just that. And then finally, we'll take a look at bringing AI into the physical world, thinking about how AI can move about the physical world and what that might look like, whether it's the form of robots or self-driving cars or other engineering constructions that can move around the world, and thinking about the kinds of AI algorithms and strategies we need to be able to solve those kinds of problems too. So AI is not just one problem. It's not just one algorithm. It's a really wide range of ideas and strategies and algorithms. And the goal of this course is just to expose some of that to you, to give you a sense for the kinds of strategies that AI can use in order to do this kind of problem solving. And all of these problems we term artificial intelligence or AI. But today's focus is going to be all about playing, and in particular about playing games. And AI playing games might seem very different from the kinds of AI that you might have experienced, or maybe you're familiar with AI in the form of chatbots or self-driving cars or image and video generation. But it turns out that playing games was one of the earliest areas of research into AI. That when we were first trying to think about how could we make computers intelligent, one of the first places we started was looking at games like chess and other types of strategy games, and thinking about how could we build AI that can play these kinds of games well. And it turns out that one of the reasons for that is that games offer a simpler environment for AI and computers to be able to work with. There are only a limited number of pieces on the board, so the world of a game is a much simpler world than the real world with all of its complexity. But even still, many of the ideas, many of the algorithms that go into getting AI to be able to play games well are the same kinds of ideas and strategies and inspirations we'll use to be able to build AI to solve many other kinds of problems too. So even though we're starting in the world of game playing, we'll soon see that these kinds of ideas are useful in a really wide range of scenarios too. And so we might try to start with games like this, games like chess that have a lot of enormous complexity to it. But actually what we'll do today is start with an even simpler game. We'll start with a game called tic-tac-toe, or depending on where you live, you might call it noughts and crosses, where the idea is that we're going to place X's and O's on this 3x3 grid and try and get 3 in a row. And so I'll talk you now through some of the rules of tic-tac-toe if you're unfamiliar with it, and then we'll start to think about some of the strategy that we can use in order to play that game well. And so that would be the break to move us into cutaway demo number 1. So I have here a tic-tac-toe board. Tic-tac-toe is played on this 3x3 grid, and there are two players. There's the X player, and there's the O player. And the players take turns placing X's and O's on any of these empty squares in the grid. So X, for example, might go first and place the X in the middle here, and then O can take any one of the remaining empty squares, and then X might take another empty square, and then O might take another one too. And the goal of the game then is to get 3 of a kind in a row. So X wants to get 3 X's in a row, O wants to get 3 O's in a row. So if X were to go here, for example, then X would win the game. X has 3 in a row going across the middle here. And there are multiple different ways to get 3 in a row. You can get 3 in a row by going 3 horizontally, left to right, across any of these rows. You could also get 3 in a row vertically, going up and down. You could also get 3 in a row going diagonally, either along this diagonal or that diagonal over there. So all of these are different ways to win the game of tic-tac-toe. But now that we have the rules in place, let's try and think about some of the strategy. And before we try to encode the strategy of this game into a computer, we can start by formalizing our own human strategy. How would we try to play this game in a way that allows us to win? Well, let's take a look at a few possibilities. Let's take a look at a board that looks something like this. And imagine that you are the X player, and it's your turn to make a move. Where would you choose to go? And well, if you look at this board, hopefully it's pretty clear that if X chooses to go in the bottom middle here, well, then X will get 3 in a row going up and down here, down the middle. And so that leads us to a strategy, or at least a question that we can ask when playing the game. That a reasonable question to ask might be, all right, well, if I can get 3 in a row, I should look for that first, and then I should play in the square that allows me to get 3 in a row. But not every position is going to be like this. Not every position is going to give us the opportunity to get 3 in a row right away. For example, we might be in a situation like this. Here, it's not directly possible, if you are the player playing X, to get 3 in a row right away. I have 2 in a row here, but my 3 in a row spot is blocked by the O player, so I can't directly play in the upper left. But if you try and think about what the right move to make is, hopefully you notice that your opponent, the O player, they are in danger of getting 3 in a row soon. If O got one more turn, O would be able to play here on the middle left and get 3 in a row going up and down. And so if we're the X player, we should probably try to block them. So that might be another strategy. Look for ways that we can get 3 in a row, but also look for ways that we can block our opponent from being able to get 3 in a row too. But even still, there are some options where there might be game situations where that's not a possibility either. For example, something like this might be a situation where X doesn't have a direct way to get 3 in a row. There's no square I can play in that gets me 3 in a row right away. But also, O is not in danger of getting 3 in a row right now either, so there's nowhere directly for me to try to block. And yet still, if you look at the position, it turns out there are some moves that are going to be better than other moves. And it'll take a little bit of strategy for us to think through where should we try to go and how should we try to plan our moves if we're going to try and play a move that's going to allow us to win. So it's this kind of strategy, these kinds of questions, that I want us to start thinking about a little bit formally so we can come up with a strategy that we can encode inside of a computer to allow a computer to be able to play a game like this too. So now that we've seen a little bit of the strategy for what gameplay in tic-tac-toe might look like, let's try and encode that strategy in a way that a computer might be able to understand. So we'll start by looking at an example tic-tac-toe board. We saw a position like this, and the question we decided was worth asking ourselves was, is it possible for me to get 3 in a row on this turn? If I'm playing X and I can get 3 in a row on this turn, well then I should play in the square that allows me to do that. And so we might represent that as a question in order to play here. We might ask the question, sorry, can we back up from the beginning of that again? I forgot there were a couple extra slides there. So now that we've seen what it might look like to play a game of tic-tac-toe, we can try and describe what the strategy would be for playing this game, so that we can take that strategy and put it inside of a computer so that computers could play this game too. So we'll start with an example position, a position like this. And what we decided was that in a position like this, the question worth asking ourselves was, is it possible for me to get 3 in a row on this turn? If I'm the person playing X's, then I might notice that I can get 3 in a row on this turn. And so if so, then I should play in the square that allows me to get 3 in a row, and that's going to result in me winning the game. And so we could represent that as a question we might ask, like, can X win on this move? And depending on the answer to that question, that's going to lead to some additional logic or some additional decision making that we might then want to make. If the answer to this question is yes, if we can win on this move, well, then the action we should take is we should play in the square that allows us to get 3 X's in a row. But the answer to that question won't always be yes. Sometimes we'll be in a position like this, where there's no direct way for us to be able to get 3 X's in a row, where instead the question that we were asking ourselves was, all right, well, can we block my opponent from getting 3 in a row? That if my opponent is the O's, if O can get 3 in a row, well, then I better play in the square that blocks them from getting 3 in a row to make sure that they don't win on their next move. And so that, too, is a question that we might ask here. I might ask the question, can O win on the next move when it's their turn? And again, if the answer to that question is yes, that gives us an action to take. In this case, the action we want to take is we want to play in the square that's going to block O from being able to get 3 in a row. If the answer to that was no, though, if we can't win on this move and we can't block our opponent, then the strategy is a little bit less clear. You might think about the strategy. You might be able to come up with some other questions that we might be able to ask, but it's not immediately obvious, at least from looking at examples like this. But still, the nice thing about describing logic like this in terms of questions and what to do based on the answers to those questions is we can take this kind of diagram and turn it into code. And what I'm going to translate this into now is something that we call pseudocode. Pseudocode is something that looks a little bit like code. It would be easy to turn into a programming language, but it's not a real programming language. It's just an English-level representation of what the logic in code might look like. So if we were to turn this into pseudocode, we might say something like, if X can win, well, then the action we should take is play the move that gets 3 X's in a row. And otherwise, if O can win, then we should block 3 O's in a row. But again, as we translate this into code, we're running into a problem, which is that if neither of these is true, otherwise, else, we're not entirely sure what to do. It's not immediately obvious, at least based on this diagram, what action we should take if we can't get 3 in a row and we can't block our opponent from getting 3 in a row. So let's take a look again at an example of a board that looks like that. Here's a position where there's no immediate way to win, and there's no immediate way to block O from winning. So what can we do? We've got a bunch of different options, and we might try to start evaluating them, figuring out what's good and what's bad. For example, I might try and play an X here in the bottom middle, but that doesn't seem to do me a whole lot. It's not really threatening to get 3 in a row. So maybe that gives you an idea for a strategy. I could say, OK, let me play a move that at least threatens to get 3 in a row. For example, I could play over here in the middle left, where I'm threatening to get 3 in a row going left to right, where if I get one more move, I could play an X here, and then I would win the game. Or I could do a similar thing by playing an X up here in the upper left corner, where again, I'm threatening to get 3 in a row going diagonally here. If I got one more move, I could play an X here, and I'd be able to win the game too. But it turns out none of those are the best move. The best move would be something like this, playing here over on the middle right. And you might look at this board and think to yourself, like, why is that one of the best moves in this position? Well, it turns out that it's threatening to win in 2 different ways. That I am potentially getting 3 in a row going left to right here. And I'm also potentially getting 3 in a row going up and down along the right side here. And O can only block one of them. And so we might imagine both ways that this game might go. For example, O might try to block me from getting 3 in a row going left and right. O could play over here on the left. But if that were to happen, well, then X would just be able to play in the bottom right, and X would get 3 in a row going up and down there. But alternatively, if O tried to stop that from happening, if O decided to play in the bottom right here to stop X from getting 3 in a row, well, then X has another way to win. X was threatening to get 3 in a row going left and right, so X could play here over on the left side, and X would be able to win there too. And so regardless of which option O tried to take, X would still be able to win. And this is the kind of logic that you and I could come up with if we were trying to play the game. We consider all of the possible things that could happen. We consider both what our opponent might do next and also how we might then respond to that. And so the goal then is not for us to come up with exactly the right set of questions to give to a computer, but ideally we want computers to be able to figure out all of this same kind of logic on their own, to have some kind of algorithm so that a computer could figure out the same kind of thing that you and I just figured out too. And so the algorithm that we'll use to do that is an algorithm called minimax. Minimax is a general game-playing algorithm where the idea is that we could give to a computer or an AI the rules of a game, like the rules of tic-tac-toe, and the computer could figure out how to play that game. It could figure out a good move to make, a good strategy to follow in whatever game position it finds itself in. And so how are we going to do that? How are we going to take something like a game and turn it into something that a computer can understand? Well, a game has a lot of human concepts. It has ideas like winning and losing and tying a game. And those aren't things that a computer naturally understands. So what is a computer good at understanding? Well, ultimately, computers are made up of and they calculate numbers. And so one of the recurring themes as we start to think about AI and how to get computers to behave intelligently is we're going to think about translating our human concepts into numbers so that a computer is going to be able to better understand them and better work with them. And so we want to turn our ideas of winning and losing and turn them into numbers that a computer is going to be able to understand. And so what might that look like? Well, as far as a computer is concerned, there are really only 3 outcomes of a game of tic-tac-toe that we might care about. And the outcomes are either O wins the game by O getting 3 in a row, or X wins the game by X getting 3 in a row. Or it's also possible that all the squares on the 3x3 grid get filled in and nobody's gotten 3 in a row. So this would be a tie or a draw. Nobody's won this game. And these are really the 3 outcomes that we care about. There are multiple ways each of these could happen. There are multiple ways O could win. There are multiple ways that X could win. But in the end, these are the outcomes that are distinct from each other. Either O wins, or X wins, or it's a tie. And so we could describe that as O winning, a tie, or X winning the game. Those are our 3 outcomes that we care about. And what we're going to do in order to get an AI to be able to play this game is we're going to turn each of these outcomes into numbers. And so O winning, we'll go ahead and give that a value or a score of -1. X winning, we'll go ahead and give that a value or a score of +1. And if it's a tie, if nobody's won, that's going to have a value of 0. So we've taken these concepts of winning and losing, and we've turned them into numbers. And I didn't have to pick these exact numbers, but I did have to pick numbers so that I could at least describe a mathematical goal for each player. And what do I mean by that? Well, what I mean is that one of the players, the X player, who we'll start calling the max player, their goal in this game is to maximize the game's value. They want the game's value to be as big as possible. And the biggest value here among -1, 0, and 1 is that +1 over there. So what the max player wants to do is they want to get to this +1. They want X to win. But if that's not possible, and they have to choose between these two, well, then a 0 is still bigger than -1, meaning tying the game is still better than losing the game from the X player's perspective. And then the other player, the O player, who we'll start calling the min player, the min player's goal is to minimize the game's value. They want the game's value to be as small as possible. What that means is that they want the game's value to be a -1. That would be O winning in this case. But if O can't win, then at least tying the game with a value of 0, that's still better than X winning the game, which in this case has a value of 1. And so now that we've described these outcomes in terms of numbers, mathematical goals, then we can use those numbers to try and make some calculations, to give an algorithm to computers to work with those numbers to figure out a good move to make. So what might that look like? Well, first, let me give you a little bit of a pop quiz. Let me present to you a tic-tac-toe grid. Here's the tic-tac-toe grid. The game is over. And let me ask you the question, what is the value of this game board? Remember, the value is that number, either -1, 0, or 1, that describes this game state. And we said that -1 meant O winning, 0 was a tie, and 1 meant X winning. And so if you look at this game state, you see that X going up and down does have 3 in a row here. So X has won this game, so this has a value of +1. But now let me ask a slightly trickier question. Let me give you a different game board or a different game state. Here's a game state where the game is not yet over. The game's not over yet, so we don't know what's going to happen. But we can tell you that it's O's turn, so O gets to make the next move. And my question for you is, well, what is the value of this game state? Is it -1, 0, or 1? Or in other words, if both players play optimally, if both players are playing the best moves they can, what's going to be the result of this game? How should we evaluate this game board here? And well, how might we do that? You might start to think about it, but what a computer might do is a computer needs to consider all of the possibilities. If it's O's turn to make a move, well, O has 2 options. O can play here in the upper left, or O can play in the bottom middle. And so what a computer might do is a computer might consider both of those possibilities. There are 2 options. Either O can play in the upper left, or O can play in the bottom middle. And we might explore what's going to happen if we go down either one of these 2 paths. Well, if O plays in the upper left here, well, then X only has one choice for what to do next. X is going to play in the bottom middle there. And that's going to result in X getting 3 in a row. X has won the game. That, we said, has a value of 1. And, well, if this game state here has a value of 1, then this board, which directly leads to this board with a value of 1, it must also have a value of 1. So we'll go ahead and assign a value of 1 to this game state over here. And so that's this left branch of this tree that we've now considered. And now let's take a look at the right branch of the tree, where O chose to go in the bottom middle. Well, what's going to happen then? X only has one possibility for what X can do next. So X is going to play in that upper left corner. And that's going to result in nobody winning the game. Nobody has 3 in a row. So that has a value of 0. It's a tie, which means the board that leads directly to it, that also has a value of 0. And so now if we go back to our original problem, this board state over here, where it's O's turn to make a move, O is looking at 2 choices, either this choice over here with a value of 1, or this choice over there with a value of 0. And remember that O is the minimizing player. Each player is either the maximizing player or the minimizing player. And the minimizing player's goal is to make the game's value as small as possible. And so what we might do here is that O is going to look at this game situation and say, if I have to choose between 1 and 0, I'm going to minimize the value. I'm going to pick the smaller one. I'm going to pick the 0 because 0 is less than 1. And so we might assign this game state a value of 0. And so what that means from an AI's perspective is that you could give this game position to an AI, tell them that you are the O player, it's your turn to make the next move, and the AI would be able to realize by doing this calculation that the game is going to be a tie if both players play their best move, and moreover, that the best move is to play over here in the bottom middle. And it turns out we've been able to do that here from near the end of the game, but you could also do that near the beginning of the game too. You would just have many more possibilities that you would need to consider. So let's take, for example, the very beginning of the game. Imagine that the X player played in the middle, and you were to give this game state to an AI and tell the AI, here's the tic-tac-toe grid, X just played in the middle. Where are you going to go? What choice are you going to make? Well, we now have to think about what are the different possibilities. What is AI going to consider? Well, AI has 8 different options for where O could make their next move. We have 1, 2, 3, 4, 5, and then 6, 7, 8 along that bottom row over there. And so what AI might do is consider all of those possible options. We might consider what's going to happen if O plays in the upper left, and then in the upper middle, and then the upper right, so on and so forth across all of the possible options. And then for each one of those options, what we'll have to consider is all of the possible ways that X might respond to that move. Where if O plays in the upper left, well, then X has 7 different possible places where X could respond to that move. And so this part of the tree will need to branch out even further. We'll need to then consider all of the possible places where X could respond to that move, and so on and so forth. For every move that we make, what our AI is going to do when running this minimax algorithm is consider all of the possible responses to that move, and all of the possible answers to those responses, and all the possible responses after that, so on and so forth, until we've explored all of the possible ways the game could go, and then we can figure out what is the optimal move. In other words, what is the best move that we can make in any given position. And if we do that, we'll end up with an AI that can play tic-tac-toe really, really well, that'll never lose at a game of tic-tac-toe. And so this algorithm, Minimax, in theory, can play a game perfectly. But it turns out we run into some challenges as we get into games that are a little bit more complicated, that are more complex, that have more different possibilities for ways that the game might go. For example, we could consider a game like chess, a much more complicated game, many more possibilities for how a game of chess might go, and consider what might it look like to play a game of chess, and what do we have to think about when getting an AI to be able to play a game like chess too. All right, so I have a chessboard set up here, and we'll use this chessboard to think about the number of possibilities there are for playing a complex game like a game of chess. And so maybe we can start by playing a game of chess. Does anyone want to play a game of chess against me? David, would you like to play, if you'd like to come up? We can play a game of chess against each other. I'll take the white pieces, and I'll make the first move, and maybe move my pawn here. All right, you moved your pawn too. I'll take this pawn and maybe move it there. All right, and I think if I move my queen here, that is checkmate. So the game is over. But thank you for playing. I appreciate it. But that was just one way this game of chess might have played out. It turns out there are many ways to play a game of chess, and so we can start to think about how many possibilities there really are. And let's start with just the very first move of a game of chess. If you're unfamiliar with the rules of the game of chess, each player has 8 of these pieces that we call pawns. And a pawn on their first move, each pawn has 2 choices. A pawn can move forward 1 square, or a pawn can move forward 2 squares. So if I have 8 pawns, each of which has 2 different possibilities for how it can move on the very first turn, that's 16 different possibilities for how I could try to move the pawns. But it turns out I also have a couple of other moves. I have 2 of these horse pieces called knights, and each of those knights also has 2 possible places where the knight could move. The knight could move here or here, and then this knight could move here or here. So I have 16 different possible pawn moves, plus 4 different possible moves with my knights, for a total of 20 possibilities. So there are 20 possible ways that I, as the player with the white pieces, can make my very first move in a game of chess. And then if we think about the first move for the player with the black pieces, they have exactly the same choices. They have 8 pawns, each of which has 2 possibilities, so 16 possible pawn moves, plus 4 possible knight moves. The black pieces also have 20 different possible ways that the black pieces can play their first move as well. So if the white pieces have 20 options for the first turn, and the black pieces also have 20 options for their first turn, that's 20 times 20, or 400 different possibilities just for each player taking one turn. Already quite a number of possibilities, and chess games can often go on for many, many more moves than just that. And so you can imagine the number of possibilities really starts to grow and might become a bit of a challenge for a computer to be able to deal with. And chess isn't even the most computationally complex among games. There are games that are even more complex than just this. David, if you'd like to move the chessboard out of the way, I can show you another game. This is an ancient board game called Go, popularized in Asia. And the idea of Go is that it's played on this 19 by 19 grid, where instead of an 8 by 8 grid, like a game of chess, in Go there are 19 intersection points going across this way, and then 19 points going up and down this way, for a total of 19 times 19, or 361 different places where a player can play on their first move in a game of Go, for example. So if I'm playing with the black stones, let's say, I have 361 options for where I can play my first stone. And then there are 360 remaining options for the white stones to decide where they want to place their first stone. And so that, just taken in total, is more than 100,000 possibilities just for these very first 2 turns by the black player and the white player there. And again, a game of Go goes on for many more moves than just that. So as the games have more and more possibilities, as there are more possible ways they can branch, as they go on for more and more moves, the number of possibilities just grows and grows and grows. They grow exponentially, in a sense, to use a mathematical term. And as a result of that, we're going to need some strategies to figure out how do we get a computer to be able to play these kinds of games like Go or like chess well too. So now let's take a look at comparing tic-tac-toe and chess a little bit more directly to think about how their number of possibilities compare, and how then we can get a computer to be able to play those games well. And that's that demo. And we'd move back to the slides. Yeah, I can. So let's take a closer comparison then. Let's look at a game of tic-tac-toe, and we'll look at a game of chess, and compare how the number of possibilities grows as we continue to play out that game from one move to the next move to the move after that. And so we can imagine, what are the possibilities after just one turn in a game of tic-tac-toe? Well, in tic-tac-toe, we've got 9 different options for where you can play on the first turn. And so there are 9 possibilities for where that first turn might happen in a game of tic-tac-toe. Meanwhile, in a game of chess, we discussed there are 20 different possibilities for how you can make the first turn in a game of chess. So after one turn, 9 possibilities in a game of tic-tac-toe, a little more than double that for a game of chess, 20 different possibilities. But now let's consider possibilities after 2 turns, after x gets a turn and then O gets a turn, or after the white pieces get 1 turn and then the black pieces get 1 turn. Well, in this case in tic-tac-toe, after x has taken 1 spot, O has 8 remaining places where O can place their O. And so that leads to 9 times 8, or 72 possible ways this game could play out in a game of tic-tac-toe after just 2 turns. Meanwhile, in a game of chess, we described that the player with the white pieces, they have 20 different options. The player with the black pieces, they also have 20 options. So after just 2 turns, there are 20 times 20, or 400 different ways that a game of chess could play out. And we can continue that calculation. Imagine that after 3 turns, how many possibilities are there? We're now comparing around 500 possibilities in a game of tic-tac-toe for how many ways could that game play out, versus almost 9,000 different ways to play out the very first 3 moves of a game of chess. After 4 turns, we're looking at about 3,000 options in a game of tic-tac-toe versus 200,000 options in a game of chess. And we can continue playing this out, 5 turns, 6 turns, 7, 8, and then 9 turns. After 9 turns, the game of tic-tac-toe is necessarily over. There's no way a game of tic-tac-toe could go on more than 9 turns, because there are only 9 squares in the tic-tac-toe grid. And as a result, there are about 260,000 possibilities. In other words, there are 260,000 different possible games of tic-tac-toe. If you were to ask the question, how many different ways are there to play a game of tic-tac-toe, a computer could calculate all of them by just calculating all 260,000 of those possibilities. Meanwhile, in a game of chess, we're looking at more than 2 trillion possibilities after just 9 turns in a game of chess. And this is usually only the very beginning of a chess game. Chess games often go many more turns than just 9 turns, for example. And so already we're seeing an enormous difference in the size and the scale of these kinds of problems. That even though 260,000 possible tic-tac-toe games sounds like a lot, a modern computer can get through 260,000 games in a matter of seconds. In a couple of seconds at most, a computer can go through all of the possible ways to play a game of tic-tac-toe to figure out exactly what the best move is going to be in any potential game board that it might find itself in. Meanwhile, in a game of chess, these possibilities are just going to grow and grow and grow, and even the fastest computer is not going to be able in any reasonable amount of time to be able to calculate all of the possible ways that a game of chess could play out as well. And so if we want to get computers that are able to play sophisticated, complex games like chess, we're going to need some better strategies. We're going to need to figure out how are we going to get computers to be able to play a game like chess well without needing to consider all of the possibilities. Without needing to play out every possible game of chess, we need to come up with some better strategy. And that's going to be especially important as the games get even more complex, as they have even more possibilities, as we consider games not just like chess, but like Go, where there are many more possible ways you could play your first couple of moves and many more possible ways you could play out a game of Go. It's going to be increasingly important that we have strategies for dealing with games as they get more and more complex. And so how could we take a strategy like minimax, this kind of algorithm that considers all of my options and then all of the possible responses to that, so on and so forth, all the way until the end of the game, and turn that into something that's a little bit more tractable for a complicated game, a game like chess or a game like Go? Well, one possible modification we could make to the minimax algorithm is a variant that we call depth-limited minimax. And what do we mean by depth-limited minimax? Well, let me give you an example. Here's an example game state in a game of chess. And I'm going to represent this game state via this blue and white circle here that we're going to call a node in computer science. This node just represents some individual piece of data. In this case, the piece of data that it represents is one possible game state in a game like chess. And let's imagine that from every game state, I have 2 options for what choice I can make in that game state. In reality, in a game like chess or Go, you have many more than 2 options most of the time. But to keep things simple, let's imagine that we just have 2 options, which means that if I have 1 turn, this 1 node is going to branch into 2 more nodes. I have 2 choices for what to do on that turn. And if each of these nodes also has 2 choices for what might happen next, well, that's going to lead to 2 more branches for each one of those nodes, which means after 2 of them, I now have 4 possible nodes after considering 2 turns. And we can keep growing this tree a little bit more and a little bit more. After 3 turns, now this is going to branch into even more directions. Now we're seeing that the 4 nodes have branched into 8. If we go 1 more turn, these 8 nodes are going to branch into 16 possibilities. And if we go 1 more turn after that, again assuming that from each game state I have 2 choices for what I might choose to do, these 16 are going to branch into 32 different possibilities. And again, this is just looking 5 turns ahead when I only have 2 choices to make at any given point in time. Usually I'm going to have more than 2 choices. Often I'm going to have more than 5 moves ahead I potentially can look. And so we need some strategy for how to deal with a situation like this. And what we might do in a depth-limited minimax is to say, you know what? Let's not consider all the way until the end of the game. At some point, let me just cut the search off. Say, we're going to look 4 moves ahead, but we're not going to look ahead anymore. And as a result of that, that's going to lead to a situation where I can say, I don't need to consider all of the possible ways the game can go. I can just look ahead a few moves and then stop there to keep the possibilities a little bit more limited. I'm going to pause, get some water, and then I'll pick up from there. So if we use this strategy, if we say we're not going to use minimax and search all the way until the end of the game, but instead we say we'll look ahead a few moves, maybe 5, 6, 7, 8, 9, 10 moves ahead in the game, and then we're going to stop, what do we then need to think about? Well, remember that at the end of minimax, once we've explored all the possibilities and we've gotten to the end of the game, at that point we were able to determine the value of the game. For example, in tic-tac-toe, we were able to say that the value of the game was -1 if O won the game, 1 if X won the game, and 0 if it was a tie. And those numbers we could then use for comparison to be able to say this end state is better than that end state, and so we should prefer one option over the other. If we use this depth-limited approach, though, where we say, in this case, only look ahead 4 turns, and don't look ahead 5 or more because we don't want this tree to grow too big, we don't want too many possibilities for us to have to explore, well, we've run into a little bit of a problem, which is that odds are most of these nodes are going to represent game states that are not yet finished yet. The game is not yet over. There are more possibilities that we could keep adding, but we've decided to limit our depth. We're not searching all the way to the end of the game. We've got these game states that are in the middle of the game, and we still need to be able to evaluate who do we think is going to win the game, who's doing a better job, so we know which nodes are better than other nodes. In other words, which game states should we try to go towards, and which game states should we try to avoid. We need some way to evaluate these game states to figure out how good or bad they really are. So when using depth-limited minimax, what we then need is something that we call an evaluation function. And what is an evaluation function? Well, an evaluation function is something that's going to take as input a game state, like the current position in a game of tic-tac-toe or a game of Go or a game of chess, and it's going to produce as output what it thinks the value is going to be. Before, when we used minimax all the way to the end of the game, we knew for sure. We knew definitely x is going to win, definitely O is going to win, definitely it's going to be a tie, and we assigned numbers to those. In the case of an evaluation function, the game's not yet over. The computer might not know for sure, but we want the computer to be able to make a good guess, some kind of a heuristic, so to speak, to be able to estimate what we think the value of this game state is going to be. And so what might that look like? Well, let's take a game like a game of chess. Here is a game of chess that is not yet over. And let's try and imagine, who do we think is doing better in this game of chess? Is it the player with the white pieces, or is it the player with the black pieces? Well, even if you don't know the rules of the game of chess, we might be able to come up with some kind of an estimate here. Because even if you don't know the rules, you might have an intuition that if you have more pieces on the board, that's probably better. You've got more pieces that you can attack with, more pieces that can do things in the game. And so one evaluation function, one very simple evaluation function we might use, would just be to say, count up the number of pieces that each player has. In this case, other than the kings, we're really just looking at pawns here represented on the board. And so if we were to count them up, we would say that, all right, white has 1, 2, 3, 4 pawns. So white's got 4 pawns in this particular game state. And the player with the black pieces has 1, 2 pawns. And so if white has 4 pawns, black has 2 pawns, well, 4 is greater than 2. And so the estimate our evaluation function, our very simple evaluation function, might say here is that white is doing better. Maybe white is probably winning this game. In this case, we said because 4 is greater than 2. 4 pawns is more than 2 pawns. Is that definitely going to be the case? Not necessarily, but it might be a pretty good guess that in many game positions, the player that has more pawns than the other player, if we're just looking at counting up pawns against pawns, that player might be the one in a better position. But again, this is an estimate. It's not going to be perfect. There are going to be situations where this doesn't perfectly capture what the right answer is going to be. For example, I might give you a different chess position, a position like this. And if you were to apply my same evaluation function that I just gave you to a board like this, well, here's how you might count that up. You might say, all right, the white pieces, they have 1, 2, 3 pawns. So that's 3 against only 1 pawn over here for black. So 3 greater than 1. Again, we might here say, all right, white must be doing better. 3 is greater than 1. But it turns out that the game is not quite as simple as just who has more pieces on the board. It also matters where those pieces are on the board relative to each other. And in this case, if you know a little bit more about the rules of chess, you might notice that this black pawn is very close to making it to the end of the board. And when a pawn makes it to the end of the board, it can become a queen, become much more powerful. And so in this case, even though the white player has more pawns than the black player, because of where those pieces are, which our evaluation function is not currently taking into consideration, this pawn is actually much stronger. And actually, the black player, they are the ones who's winning this particular game. And so the better our evaluation function is, the more accurate it is at trying to estimate how good or bad a particular situation is, the better we're going to be able to play this game. Because the evaluation function is how our depth-limited minimax algorithm is going to evaluate how good or bad a particular game state is. And that's going to direct its decision making. That's going to result in it trying to make a good move as best as it can. And part of the art of designing a good game-playing AI is giving AI a good evaluation function, an evaluation function that will allow it to play this kind of game well. And in more recent times, we've seen advances where AI can try and come up with some of these evaluation functions on its own. So we don't need to tell AI exactly what evaluation function to use, but AI can, either through trial and error or by learning, figure out what a good evaluation function to use might be. And so this kind of approach, this depth-limited minimax, is one way we can deal with this complexity, this problem that there are many, many different possible ways that a game could play out. We can't consider all of them. And so we need some strategies to figure out how are we going to deal with these situations? How are we going to limit the number of possibilities that we need to consider? It turns out there are other strategies too. And one that's proven incredibly popular for AI playing games is something known as Monte Carlo tree search. And so what is Monte Carlo tree search? Well, I'll introduce it by way of an example. Let's imagine we're playing a game, like a game of tic-tac-toe. And I am considering 2 different moves. And my question is, which of these 2 moves is better? So here's the game state I find myself in. And the moves I want to consider are these 2. I want to consider what happens if x plays in the bottom middle here. And I also want to consider what happens if x plays in the bottom right. Both of these are possible moves. Neither one immediately gets 3 in a row. Neither one like blocks O from getting 3 in a row. But my question is, which one of these two options is better? And we'd like for the computer to be able to figure that out. Now, of course, in this case, a computer might be able to calculate all the possibilities for the game, as we've seen before, and figure it out for sure. But in this case, I want to use tic-tac-toe to introduce an algorithm that'll work even for more complex games, algorithms that'll work for chess and Go and games like that as well. And so if we take just one of these possibilities, say x moving in the bottom middle here, and we want to say, what might happen if x were to choose to go there? One option we have, rather than consider all of the possibilities, is just randomly play out this game. In other words, randomly choose moves for each player and see what might happen at the end of that game. And if I were to do that, well, I'm just going to randomly pick moves for both players. And in this particular game, x won. X got 3 in a row. Now, that doesn't mean x is always going to win this game if x plays in the bottom middle, because I was just picking randomly. For both players, I was just choosing random moves, not being strategic, not trying to pick good moves, just choosing randomly. And because it was random, if I tried it again, I might get a different outcome. So even though when I randomly played this game out, it ended up with x winning, that doesn't mean that this is great for x. I need a little bit more information, a little bit more data. And so what we might do, though, is rather than just randomly play out the game once, I could randomly play out the game multiple times. Let me try this a few times and try playing this out again and again and again from the same position, but randomly play it out and see what different possibilities emerge. And so if I try that, randomly play out this game a few different times, you'll notice we get some different results. Like sometimes, yeah, x wins the game. And in other times, O is going to win the game. And in other cases, it ends up being a tie because I'm using randomness here. I'm not like strategically picking what move to play. I'm just saying randomly play out the game. And if I do that again and again, kind of like a roll of the dice, every time you get a different die roll, every time I get a different way this game potentially can play out. So given that it's all random, is this actually useful? Well, one thing we might say is if we randomly play it out a lot, and despite the fact that we're randomly trying different things every time, if x is winning a lot in a lot of those random playouts, well, maybe it's a pretty good situation for x. And if we randomly play out the game a lot, and O wins a lot of those playouts, well, then maybe that's a pretty good situation for O. And so what we could do is imagine taking both of these two options, x going in the bottom middle, x going in the bottom right. And if I wanted to compare these two possible moves, then what I might do is play them out a bunch of times each and just tally up for each one of these options. How often does x win? How often is it a tie? How often does O win? And so I'll go ahead and randomly play these two out 100 times each, 100 random possibilities for each of these two possible moves, and we'll see what happens. And if we play it out 100 times, we notice that in this case, when x played in the bottom middle, x won 46 of those games, O won 33 of those games, and it was a tie in 21 of those possibilities. And meanwhile, when x played in the bottom right here, x won 75 of those games, O won 19, and it was a tie in 6 of those games. So it seems like more often when x plays in the bottom right, x is doing better. X won 75 games over there, as opposed to just 46 games over here. And so as a result of that, as a result of these random playouts, we might conclude that x playing in the bottom right might be better. And the more playouts you do, the more accurate of an answer you might be able to get. But the advantage here is that if you're playing a complicated game, something like chess or Go, where there are just too many possibilities to play out all the possible ways the game could happen, you can just randomly sample, randomly try some of the ways the game could happen. And if you try for longer, you'll get more data and be able to draw better conclusions. But by just playing out a few different options, even without playing out them all, we might get a sense for which one option is better than which other option. And we can even be a little bit more intelligent in terms of how we consider all of the possibilities. Because odds are we're going to have lots of possibilities to search, and we're going to have to decide which possibility are we going to try at any given time. And ideally, we want to spend our computational resources. We want AI to spend its effort on the most promising options, the ones that are most likely to lead to a good outcome. And so what might that look like? Well, imagine that we're playing this game, again, starting from this node, representing some game state. And I want to consider two different possibilities, two different moves that I could choose to make. And I want to consider which one is better. And so maybe I start by playing out this move over here on the left and see what happens. And maybe I find out that when I randomly play that out, this time I lost on taking the option to the left. Well, I say, OK, that wasn't so good. Maybe I should try something else. Maybe I should try this path over here to the right. And say, what happens if I do this? Well, if I do that, maybe I randomly play it out, and choosing the option to the right, choosing that path, results in me winning the game. And OK, that seems promising, so maybe I'll try to do that again. Maybe I'll try playing out the right again, try another random way the game could go from here and see what happens. And maybe that results in another win. Now I've won twice on this side. Maybe I'll try it again and win 3 times on that side. And I keep saying, all right, this seems to look pretty good. Maybe I should keep trying it. So maybe I try it a 4th time, and this time I lose. And I say, OK, 3 wins and 1 loss over here, as opposed to 0 wins and 1 loss over here. And now the question is, which path do I choose to play out next? Which one do I want to try now? Do I want to play out the move to the left, or do I want to play out the move to the right? Well, one way you could think about this is you could think about it in terms of the success rate. How often do I win a game? Where over here in the action to the right, I won 3, I lost once. So I've got like a 75% win rate if I choose the option to the right. Whereas over here, 0 wins, 1 loss, that's a 0% success rate. I've never won by taking the option to the left. And so that might get you thinking, all right, the one to the right, that's probably the more promising one. Maybe I should just keep trying that. But on the flip side, you might also say, you know what, this option to the left, even though it has a lower success rate, I've also explored it less. I've only tried it 1 time, whereas in the option to the right, I've tried that a number of times now. And so maybe it's not as good now, but maybe it's just because I haven't explored it enough. Maybe I should explore it more. And if I explore it more, then maybe it'll turn out to be even better than the option to the right, and I just don't know it yet. And so maybe I do try the option to the left, and now it turns out that I won on that side, and so maybe it's better than I thought it was. And so this represents one of these fundamental trade-offs that we have to make when we're evaluating AI, when AI is trying to make decisions and trying to decide what it's going to do. On one hand, it can explore. It can try and do something where it's not sure if it's going to lead to a good outcome, but it can try something a little bit new, something it hasn't explored as much before, and see if it leads to a better outcome. And meanwhile, it can also exploit its existing knowledge. It can use the fact that it knows that this path to the right looks pretty good. It's got a pretty good success rate. And so maybe we want to continue trying going along that direction to see what kind of outcome it leads to, because it seems to be a pretty promising direction so far. I'll pause there and then pick up with the next section after that. So this trade-off between explore and exploit shows up all the time in AI, where we want AI to explore new possibilities, to be able to gain new knowledge, but we also want AI to be able to exploit its existing knowledge, use the things that AI has already learned to be able to make good decisions. And this shows up not just in the world of game playing, but all sorts of places in AI. When we want AI to be able to discover new possibilities and make good decisions and figure out what to do in a given situation, it happens in our own everyday lives too, even outside the context of AI. If you imagine going to your favorite restaurant, you might exploit your existing knowledge and buy the meal that you know you like, that you know you've gotten before, or you might choose to explore something new and maybe you'll find something you like even better. And ultimately what we want AI to do is to be able to balance these two things. To explore sometimes, to be able to find good options, but also to use the knowledge it already has to exploit that knowledge to be able to then make good decisions. And so we can use this kind of technique in something like Monte Carlo tree search to be able to search through a wide range of possible options for how to play out a game or solve some other kind of problem, and use the results of that to be able to make some kind of decision too. And so these are some of the strategies we might use for thinking about how to play a game like tic-tac-toe or chess or Go. But if you think about how you and I might learn to play a game and learn to play a game well, there are many different ways you might do that. One way is I could give you the rules of a game like tic-tac-toe, and you could study the rules, and you could come up with a strategy, and you could figure out what a good strategy might be. But another approach is that you might learn about this game through experience. You might try playing a game of chess, and maybe you lose your first game. But you learn a little bit from that experience. You learn what not to do next time. You learn how to do better. And the next time, you play a better game. And so one big area within artificial intelligence is not just about giving AI the tools to come up with a good strategy. It's giving AI the ability to learn, to be able to take information, learn from that, and get better at being able to solve some kind of problem or perform some kind of task. And we call this subdomain within artificial intelligence machine learning, or ML. ML is all about giving computers the strategies and the algorithms and the techniques they need to be able to learn from data, or to be able to learn from experience, for example. And the particular kind of machine learning I want to talk about now is something called reinforcement learning. Reinforcement learning is all about learning through punishments and rewards, that you try something and you do it well and you get some reward for that, and you mean you can do more of that next time. Or you try something and it doesn't go well and you get punished for it. And this is very similar to the way that you and I might learn, for example, if you're learning how to cook, for example. You might try to cook something, and if you cook something and it turns out really well, then you might learn from that experience and you might do more of that next time. Do something that looks like that in the future, and maybe it'll still taste good in the future. And if you cook something and it doesn't turn out particularly well, then maybe you learn, you know what, let's not do something like that. You learn what to change. You learn from that experience. You're punished for your experience, and you figure out how to do a better job in the future. And so reinforcement learning is a lot like that too. The idea then is we're going to get a computer to be able to learn through experience and learn through punishment and reward. And you might initially have the question of, like, what does it mean to reward or punish a computer? But we'll explore what that looks like in just a moment too. But let's take a look at another game where reinforcement learning might prove to be an interesting strategy. We'll take a look at this snake game, which you might be familiar with from like old video game consoles or mobile phones, for example, where the idea is that we are this snake navigating this grid. And we're trying to eat as much of the food as we can. There's some food here. And every time we eat the food, the snake gets longer. But what we want to do is avoid crashing into any of the walls. So we can try playing this game. The snake's navigating around. It's eating the food. Every time it gets the food, the snake gets longer. But if it ever crashes into the wall, well, then the game's over. The game stops, and we've lost the game. And you could imagine, what would it take to get a computer to be able to play this game well? Well, it's going to need some notion of like where the food is. You want the snake to navigate towards the food while being careful not to crash into the wall, being careful not to crash into itself as the snake starts to get longer too. And that's a fair bit of logic that we'd have to encode inside of a computer. But where we might start is the way that you and I might start when we are playing a game for the first time, which is that we could start completely randomly. We could say, what would it look like if we were to train the AI to play this game completely randomly? We didn't give it any kind of strategy. We just said, at any given point in time, make a move and see what happens. And if we were to do that, if we were to train this AI completely randomly and say, go ahead, try playing the game, here's what might happen. It's kind of wandering aimlessly. It's not really going towards the food. It's just randomly moving around. And eventually, if it randomly moves around, eventually it's going to crash into the wall, and it's going to lose the game. So this AI is not particularly good at playing this game, nor should it be, because what we said is just behave randomly. We didn't give it a very good strategy. But the idea now is that every time it plays this game, what AI can do is it can learn from the experience. It can learn from any action that it takes. It can look at what is the result of that action. And based on the result of that action, it learns what to do more of next time. And it learns what to do less of next time, too. And so how could we take these ideas of playing this game and turn it into something that the computer can understand? Well, recall that when we were playing tic-tac-toe, what we did is we took the outcomes of a game of tic-tac-toe and we turned them into numbers. We said that X could win the game, or O could win the game, or it could be a tie. And we assigned numbers like 1 or -1 to 0 to each of those possibilities. We could imagine doing something similar for each of the possible actions that the snake could take here too. And it turns out there might be like 3 different actions that we care about that the snake might take in a game like this. One action might be if the snake is here and it moves to the right, it might crash into the wall. So that's crash. If it crashes into the wall or it crashes into itself, that's one possible result of an action. Another possibility is the snake is here and it chooses to move and nothing happens. It just decides to move and it didn't crash and it didn't get any food, but it just chose to move 1 space forward or 1 space in one direction or another in this grid. And another possibility is if the snake is right in front of some piece of food, such that if it moves forward, it'll end up getting that food. Then the snake can move forward, it can eat that food, and that's something good, presumably. You want to try and eat as much as you can. We want the snake to grow longer and longer and longer to get a higher score in this game. And so these are the 3 possible outcomes of a particular move. We might crash, we might just move, or we might eat. And then we can assign to each one of those possibilities some kind of a score. We could say that crashing, that has a score of -100. It's really, really bad for the AI to crash, so we'll give that a big negative score. Moving is kind of neutral. It didn't crash, but it also didn't get any food. We'll go ahead and give that a score of 0. And eating, that's pretty good. It's not as good as just like not crashing, but eating is still pretty good. And so we'll say, all right, we get 10 value 10 or a score of 10 every time you eat something, for example. And so we've got these 3 possible moves, and I've assigned some scores to them. I didn't have to choose these exact scores. I could have chosen different values, and it still could have worked. But we do have to be a little bit careful about how we choose those values. And we'll see that in a moment, too. I don't totally understand this question. So now we've considered the different kinds of actions that you might take and the result that might happen from those actions. You might take an action that leads to crashing into a wall, which would be really, really bad. You might take an action that results in eating some food, which is good. Or we might have an action that does neither of those things, which in a sense is kind of neutral as well. And so let's imagine now how we could take these kinds of ideas and give the computer the pieces that it needs so an AI can figure out how to learn from playing this game, learn from experience, and ultimately learn how to play this game well. And the first concept we need is some notion of the game state, that our computer, our AI, needs some representation of the current state of this game board so it understands all the pieces, so it knows how to predict what might happen from this game state and what actions to be able to take in this state. And there are many different ways you could choose to represent this game state, but one possibility would be to represent it based on some number representing how far away the head of the snake is from walls in any given direction, maybe some numbers representing how far left and right and how far up and down from the snake the food is. There are many different choices for how you could represent it, but ideally the state should have enough information so that we know what kind of action might be good and what kind of action might be bad. So some notion of how far away the walls are and how far away and in what direction the food happens to be. So the state is one concept we need to keep in our minds as we think about getting an AI to be able to play this game. The next concept is the concept of an action. The action is something that we choose to do in that state. The action might be move to the left, the action might be move up, the action might be move down, but some kind of action that we take inside of that state. And as a result of taking a particular action in a particular state, what we're going to do is we're going to give AI some kind of a reward. And the reward is just going to be a number. Like a positive reward is good, and a negative reward is like a punishment. It's something bad. In this case, we didn't crash, we didn't get any food, so it's kind of neutral. We'll go ahead and give that a reward of 0. But then the idea is that we now have this concept of a reward that results from taking an action in a particular state. And so what we're going to have the AI learn, ultimately what AI is going to learn to do, is it's going to learn how to take a state and an action and predict, based on the state and the action, what the reward is going to be. This is the thing that we want AI to then be able to learn, to be able to say that in whatever state I'm currently in, where I know where the walls are around me, I know where the food is, and I can learn if I take this action, like keep going forward when there's a wall ahead of me, that's going to result in crashing, that's going to result in a big negative reward, otherwise known as a punishment. And so from there, I can learn not to do that in the future. And the goal is to learn for all of the possible states and all of the possible actions how to predict what the reward then is going to be. And there are multiple ways, again, that the computer could choose to do this, but this essentially is the fundamental idea of what we're trying to learn via this process of reinforcement learning in this case. And we call this process, this mapping of the state and the action to the reward, this reward function. So what we're trying to predict is this reward function that tells us what the reward is going to be depending on what the outcome happens to be. And so again, what might we choose as the output for this reward function? Well, maybe crashing, we say that has a reward of -100. Moving, we said that has a reward of 0. And food, we said that had a reward of +10. And this is nicely ordered in the sense that the better options are at the bottom. We want the food. Then moving is still better than crashing in some sense. But again, I didn't have to choose these exact numbers, but I do have to be careful. Because if what the AI is trying to do is the AI is going to try to maximize its reward. It's going to try and get as many of these reward points as it can by taking whatever actions it can in the state that it happens to find itself in. Then what the AI is going to do is whatever is going to result in just increasing that reward as much as possible. So imagine for a moment that I had chosen slightly different numbers for what to give as rewards for each of these possible options. Maybe I had said crashing is 0, moving is 1, and food is 10. This maybe initially still looks kind of reasonable. We still have food as the most valuable thing, and we still have moving as a little bit better than crashing. But if you imagine what might happen if we were to use this reward function and give it to an AI and say, use this information, play this game, learn from experience, and figure out what action to take in the state for any given point in time, what we might end up with is a situation like this, where we end up with the AI snake that just moves in circles over and over and over and over again, infinitely, just circling and circling. And why might it do that? Well, remember that every time it moves, regardless of whether we gave it food or not, in this case, we gave it a reward of 1. So if it just moves in a circle again and again and again, it can just keep accumulating 1 point for every move it chooses to make, increasing infinitely, getting many, many points, and it never needs to worry about the food at all. It can still just get a lot of reward as a result of that. And it all comes down to how it's learning to map state and action to reward. If it learns that just action moving in a circle over and over and over again leads to some positive reward and it hasn't found anything better yet, then maybe it'll just keep doing that, and it'll never learn that it could actually do something better by trying to find the food, for example. And so if we're not careful about how we design these kinds of functions, how we set up these learning environments, and how we choose to reward or punish our AI, it can result in some very different outcomes. And this has had some real implication in some real world examples. Sorry, let me back up and try that again. Do what right after?
The rehearsal. I forgot that you answered my question now.
Oh, yeah, no worries.
One other question.
Yeah,
Even with your
let me grab some water while we do. So we have to be a little bit careful about how we choose to decide what rewards our AI is going to get based on the actions that it takes in any particular state. Because ultimately what AI is going to try and do is optimize to try and maximize its reward as much as possible. And at any given point, whatever state it's in, it's going to try and figure out some action to take. And again, as we've seen before, AI might engage in this explore versus exploit type of trade-off, where sometimes it might take the action that it knows leads to the best reward. But sometimes it might say, you know what, I might try an action that doesn't seem to lead to the best reward yet, but one that maybe I haven't explored as much, maybe try something random sometimes, in order to see if maybe that leads to more reward down the line. Like if it hasn't quite found a path to get to the food yet, maybe sometime later it'll try some new action that tries something different to potentially try and get the food in the future. And so depending on how we construct this setup of what reward we choose to give the AI, that's ultimately what it's going to learn, because it's going to learn to try and maximize that reward as much as possible. And if we're not careful about how we choose to set up those rewards, AI might end up doing something a little bit unexpected, where maybe if we expected the AI to always try and go towards the food, if we set it up slightly wrong, we might end up with an AI that just goes in circles again and again and again. And there's an example that I like to use that involves using an AI, and this is a real academic study that was published, that involved using AI to try and put together Lego bricks, to be able to stack one Lego brick on top of another Lego brick, and seeing how you could build a virtual robot to try and solve a problem a little bit like this. And what happens if you were to try to do that? Well, let's take a look at what happened in this particular case. So the researchers had an AI, and what they were trying to do is use this virtual robot to try and stack this red Lego brick on top of this blue Lego brick. So that was the goal, to be able to stack the red Lego brick on top of the blue Lego brick. And what they wanted the AI to do is, rather than give the AI direct instructions for how to stack one brick on top of the other, they wanted the AI to learn through reinforcement, to try doing something that would stack it. And if it worked, then great, it learns to do more of that in the future. And if it did something that didn't quite work out, if it did something wrong, then it learned from that too. It learned not to do something like that in the future too. But in order for that to work, we needed some way to decide what the reward or punishment was going to be. How do you reward the AI for being able to stack the red Lego brick on top of the blue Lego brick? And what they decided to do in this case was use what is the elevation, how far up or down is this bottom part of the red Lego brick. Like right now, this bottom part of the red Lego brick, it has a height. We call that height maybe 0, for example. And if you were to successfully stack the red Lego brick on top of the blue Lego brick, well, then the bottom of the red brick would be a little bit higher. In some units, maybe we'll call that 10, for example. It's a little bit higher. And so that would be some positive reward, and that would be a reward for the AI for stacking the red Lego brick on top of the blue brick, and then AI would learn to do more of that in the future. So that was the goal, that if we measure and give some reward based on how high can you get the red bottom of the red Lego brick, that's the reward you get for this particular scenario. And think about that for a moment and imagine what the AI ended up learning to be able to do. Well, what it turns out happened is that the AI decided, you know what, I can take that red Lego brick and I can flip it upside down. That's a fair bit easier than stacking the red Lego brick on top of the blue brick. And if I do that, well, now all of a sudden, that bottom of the red Lego brick, it's gotten much higher up than it was before. And so that's a pretty good positive reward. It can learn to do that again and again and again. It never needs to stack the red Lego brick on top of the blue Lego brick at all. I can just turn the red Lego brick upside down and still end up getting a positive reward and learn to be able to do that as well. And so that's another example of how we need to be a little bit careful about how we design AI, because we as the people who are building AI, deciding what its goals are and what it's trying to do, we have to live with the consequences of that and decide, when AI is trained to do this, what is it ultimately learning to do? And this is representative of a broader problem with an AI, this problem of AI alignment, which is all about this problem of how do we make sure that AI's goals are consistent with our goals, that what it's doing are consistent with what we think is good and what we want AI ultimately to be doing. And some of that comes down to things like coming up with good reward functions, figuring out what are we rewarding AI for and what are we punishing AI for, because whatever we choose to do, whatever we have AI optimized for, remember we've seen a couple of times now today, what AI is really good at is it's really good at optimizing and working with numbers. Whatever numbers we choose to give to the AI, that's what it's going to optimize for. And so hopefully that is going to be well aligned with what we want AI ultimately to be able to do. So that then was a look at how we can get AI to play games. And as we continue in this course, we're going to look at many more applications of AI, looking at other bigger, broader types of problems that we can use AI to solve. So this then is an introduction to artificial intelligence, and we'll see you next time.